Uh, this morning's session is devoted to quantum gravity, and I would like to welcome our first speaker, Professor Kip Thorne from the Caltech in California. And his title is Geometrodynamics.
Thank you. I won't say anything about quantum gravity. I'll remain totally classical, despite the name of the session. John Wheeler, in 1957, wrote two papers that were published one right after the other, one on classical geometrodynamics and the other on quantum geometrodynamics. And I'm going to remain totally classical in the spirit of his first paper. By way of introduction, I'd like to just note that Einstein's field equations in vacuum, if you express them in terms of the metric, solving for the metric, are famously nonlinear. However, I believe that we know remarkably little about the consequences of those nonlinearities in dynamical situations, or in highly dynamical and highly nonlinear situations. Nonlinearities elsewhere in physics give rise to a large number of fascinating and technologically important phenomena. There are solitons, solitary waves in fluids and plasmas and in nonlinear optics, breaking ocean waves, weather and climate patterns, which are sort of two-dimensional analogs of turbulence, full three-dimensional turbulence in fluids and plasmas, phase transitions in condensed matter, and in optical technology, looking at more recent, very recent developments, mode-locked lasers, which give rise to optical frequency combs, which are having a revolutionary influence on time and frequency standards. And this is just, of course, a tiny fraction of the areas where nonlinearities play a major role. But Einstein's equations are, in some sense, more nonlinear than most anything else that you meet. And so you would expect that in Einstein's equations we would also see a wide variety of interesting nonlinear phenomena. In general relativity, we do know several important exact solitonic solutions, that is, objects that hold themselves together over long periods of time, indefinitely hold themselves together, exact plane gravitational waves, and black holes, the Schwarzschild and the Kerr solutions. But learning about generic dynamically nonlinear phenomena has been an enormous challenge. In the 1950s and 60s, John Wheeler exhorted his students, among them me, and his colleagues, to probe what he called geometrodynamics. He used that phrase in several different ways. The way in which I want to use it today is simply the nonlinear dynamics of curved space-time. And I remember very well his inspiring lectures and personal conversations about what marvelous things there ought to be in geometrodynamics, and how we really should be digging in and trying to figure out how the space-time curvature behaves in these highly nonlinear situations. The decades-long struggle to fulfill Johnny's vision, I think, is worthy of historical study. And today I'll give my own parochial description of some aspects of that struggle. I'm not a historian. I have personal views based on having lived through most of this history myself, largely on the sidelines until the last several years. And this is my own personal passion now and my own personal research. And I will come to that at the end. But the history of how we got to there, I think, is rather fascinating. I'll be focusing primarily on the physical insights that we have gained or been trying to gain, rather than on the mathematical insights. But I will touch on the mathematical side of things from time to time. So as an outline, I want to talk in a little more detail about Wheeler's vision from the 1950s, about quiescent black holes then as solitonic solutions of the vacuum Einstein equations, space-time dynamics near singularities, gravitational waves, in particular the nonlinear self-coupling of gravitational waves and what is called critical gravitational collapse, Nonlinearities in higher dimensions, one simple and intriguing example, the black string instability. And then mergers of binary black holes. And finally, just a few words about gravitational wave observations as a way to make this topic actually an observational topic rather than a purely theoretical topic. So that's where I'm going. I'd like to encourage you to interrupt me or to have a discussion with me. I don't want to just lecture to you. I think there are spots in here where you may have some questions or some insights of your own. So let's have a conversation if we can. So let me begin with Johnny Wheeler's vision. I call him, maybe I should say, Wheeler was a bit formidable in his formality on one hand, and yet very approachable when you got to know him. He was always, to me, Professor Wheeler until the day after I defended my PhD thesis, when I phoned his home and I said to his wife, Jeanette, I said, could I speak with Professor Wheeler, please? And she said to me, she said, now, Kip, you defended your thesis yesterday. Now you may call him Johnny. So Johnny Wheeler's, in 1953, emerged from having devoted several years to the design of the hydrogen bomb. And he had, during that period, he had thought about where am I going to go in my career from here. And he just had decided late in that work that he wanted to embark on a quest to understand general relativity and its implications classically and especially for quantum physics. As a first step in 1952-53, he taught a course in general relativity at Princeton. It was the first relativity course, I'm told, that had been taught at the university since 1941, since the beginning of the war. During that course, he had lots of different insights about general relativity, but the one that he liked the most was the geon, a gravitational electromagnetic particle, quote particle, or a model for a particle, which he then realized a little bit later could be done purely with gravity without electromagnetism. So let me talk about it in that context. So what you imagine is you have a ring of gravitational waves propagating around like this, but it could be propagating actually on the surface of a sphere, much like Einstein's model in 1939, where he argued against the existence of a quote Schwarzschild singularity, against the possibility of black holes, by thinking of photons that travel on the surface of a sphere, totally spherically symmetric then when you look at the large-scale geometry. In this case, gravitational waves traveling around the surface of a sphere, held in by the gravitational pull of the gravitational wave's energy. So this is a nonlinear phenomenon. The energy, which is second order in the amplitude of the waves, holds the waves together. And he explored that as a possible model for an elementary particle. It was never successful. He did realize right from the outset that these waves would gradually leak out. And then later he realized that there would be a collective instability, which I don't think has ever been explored numerically, but a collective instability in which this thing would come apart rather rapidly. And therefore this can't exist in nature, but nevertheless it's an intriguing first step toward geometrodynamics. In fact, it hinted at the richness that nonlinearities can produce in curved space-time. And this particular model, in the hands of Wheeler's students, gave rise to some very powerful tools for general relativity research later on. Brill and Hartle developed the technique of two-length scale expansions in the context of general relativity as a way to make this mathematically rigorous. And then Richard Isaacson picked up on the two-length scale expansion idea as a student of Charlie Misner's and developed the theory of the stress-energy tensor, not pseudotensor, but the stress-energy tensor in a two-length scale expansion, the stress-energy tensor on scales long compared to a wavelength for the gravitational waves, which has been a tremendously important concept in gravitational wave science over the last several decades. So this all came out of the geon, but for me the important thing is this first example of geometrodynamics. 1957, among other things, Johnny began to think about wormholes. The wormholes, of course, had been studied previously by Einstein and Rosen, before that by Weil, and actually by Ludwig Flamm back as early as 1916. He imagined a wormhole threaded by electric fields, and this was his own drawing of this, a heuristic drawing, as a model for charge without charge, as he would call it, a positive charge here and a negative charge there at the two mouths of the wormholes. He, in that period, developed a particular point of view on this subject and on physics more generally, what he called radical conservatism, that one, in exploring the frontiers of science, that a good approach is to adhere to well-established physical law, in this case Einstein's general relativity theory, but follow it into the most extreme of domains. And so radical in this sense of exploring extreme domains, conservative, you stick with the well-established laws until you get into trouble. And, 1957, he wrote with Charlie Misner his classic paper on classical geometrodynamics. So it didn't have that title in the title of the paper, but it did have that as the running head in the journal, Classical Geometrodynamics. And then by himself, his first paper on quantum geometrodynamics. And he conceived then, he and Charlie Misner in that paper in 1957, conceived the idea that what you should do is give the initial 3 geometry of space subject to constraints and then evolve that 3 geometry forward in time. And these ideas then were made mathematically rigorous in the Arnouet, Desir, and Misner formulation of how one might actually do numerical relativity, solve Einstein's equations numerically, but that also gave a foundation for understanding Einstein's equations, the constraint equations, the evolution equations mathematically. But Wheeler, throughout this, had the vision that one would solve these equations numerically. And so he pushed his research group then in the 1950s and into the 1960s to move rapidly toward numerical relativity in order to understand classical geometrodynamics. In particular, in 1959, his student Dieter Brill, under his guidance and inspiration, developed the mathematics for how to generate axially symmetric gravitational waves as solutions to the constraint equations, the initial value equations. And these so-called Brill waves were ultimately implemented as initial data for numerical relativity decades later. And numerical relativists watched as if you put enough energy into a Brill wave, as the gravitational wave collapsed and formed a black hole. But it was many decades later until these were actually studied dynamically. But the solution to the constraint equations was in hand already in 1959. 1960, Charlie Misner worked out a solution to the constraint equations for a black hole where the 2 mouths of the black hole were sitting in the same manifold. And then in 1963, Brill and Lindquist gave a solution to the constraint equations for 2 black holes where the other ends of the black holes, it was actually 2 wormholes. The other, so I should have said a wormhole. So Charlie Misner built a solution for a wormhole where the 2 mouths of the wormhole were in the same asymptotically flat space. And then Brill and Lindquist did the same, but with the far ends of the wormholes in different spaces. And so these also became initial data for numerical simulations decades later. In fact, the problem of implementing the evolution equations was a big showstopper. The work on solving Einstein's equations numerically in spherical symmetry began with May and White, Sterling Colgate carrying this forward into supernova simulations, Jim Wilson at Livermore in the 1960s, spherical symmetry. And so by 1962, I remember very well I was in I guess I should back off. That was probably 63. I remember being in John Wheeler's relativity class at Princeton, and he coming back from Livermore all excited about these first numerical simulations that had been done solving Einstein's equations on computers. In axial symmetry, however, the first efforts actually were by Bryce DeWitt even earlier in 1954 when he was at Livermore as well. This was all building on the codes that were developed at Livermore for simulating thermonuclear explosions, the hydrogen bomb design work. But Bryce DeWitt said to himself that, look, in order to do the hydrogen bomb simulations that I'm supposed to be working on, I really can do them best in curvilinear coordinates. And having recognized that, he also recognized that he could use that then also to solve Einstein's equations. He didn't do much with it, but it was already as early as 54. I don't know whether it was totally independent of what Johnny was doing or not, but already as early as 54, he was thinking about it. But it was not until 1976 that successful, robust solutions in the case of axial symmetry were done successfully by Bryce DeWitt and his students Chavez Smar and Larry Smar's student Ken Epley. The big push began in 71 with success in 76. It's a long time from the time that Wheeler laid down the vision, and I'm not sure why it was so long. I did live through most of that period as a member of the community, and people weren't thinking very much about this. Johnny had offered his vision. It said we should be doing this, but people were studying black holes and other phenomena, and this just was not a priority in that period, and I'm not quite sure why. I think it wasn't that it was so hard. People didn't realize how hard it was yet. Nobody really pushed hard on it, as far as I'm aware, until Bryce DeWitt in the early 1970s. So it said, yeah.
Can I ask a question to that? Because it was then the time when people started with Penrose and others to develop a more global, a more topological view of these things. So might that have kind of shifted the perspective away from these dynamical considerations that you're talking about?
I think that could well be part of it. It was a very exciting time because of these topological methods that Penrose brought into the field, because of the discovery of quasars and pulsars, because of the modeling to try to explain quasars and pulsars. And there was so much going on, and it was you're now getting into the golden age of relativity, beyond just the initial Renaissance. And there was so much going on. This was one thing, but it was a very low priority thing that nobody was paying much attention to, except a little bit Jim Wilson at Livermore and Bryce DeWitt, and then Larry Smar, who got inspired by Bryce and really took it and ran with it. So having made, say, head-on collisions of black holes successfully and robustly, people started then to do other explorations in axial symmetry. For example, Svi Perron's classic simulation of the axially symmetric gravitational collapse to form a black hole. And it was not really, however, until roughly 1990 that a number of research groups pushed hard trying to get into 3+1 dimensional numerical relativity, to simulate situations in generic situations where you would really see geometric dynamics in its full richness. And it again strikes me as how long it took for people to really mount up the effort. There was a lot of richness to explore with axial symmetry. And so, but it really wasn't until about 1990 that people began to push hard on Wheeler's vision. Took an additional 15 years for success. 15 years of very intense work by a number of research groups, knocking their heads against walls, having no success, problem after problem after problem. And by now, in hindsight, looking back from 2005 back over those 15 years, it's pretty clear to me that the reason The primary reason that it was so hard was that we did not understand the mathematical structure of Einstein's equations in the following sense. That if you just write down Einstein's equations in what would appear at first sight to be a good way to solve them numerically, they will not be strongly hyperbolic. They don't have all of the nice properties that you would want in order to solve them numerically. You have to get into a very special gauge. You have to adjust your coordinates appropriately and be solving for the right variables. And that's a lot of work to figure out how to bring them into a strongly hyperbolic form. This was ultimately done, and Franz Pretorius worked with such a formulation. There are, most of the people even today working with so-called puncture methods are working with a formulation that is not strongly hyperbolic, but nevertheless they are having success. Perhaps a bigger issue was constraint violations. You pose, of course, the constraint equations, find a solution, numerical solution of the constraint equations. There's always some amount of numerical error in your solution of the constraint equations. And unless you formulate your equations just right, that error will grow, often exponentially, or at least as a power law. So, for example, if you're simulating two black holes going around each other, you can't get even one orbit, and the whole code crashes because the errors in the constraints, because even analytically, the errors in the constraints will grow and just wipe you out, not just numerically, but analytically. And so it took a long time to sort this out. And I think part of the issue was the arrogance of physicists, thinking that, well, they can do it by their own techniques without consulting the mathematicians. And I think consulting mathematicians in the end was an important part of bringing this under control. Let me turn to quiescent black holes now. We all know the story. 1939, Oppenheimer and Snyder studied the spherical gravitational collapse of a cloud of dust, a uniform density cloud of dust. We know that the exterior of the cloud, of the collapsing cloud, is the Schwarzschild solution. We know that, and Oppenheimer and Snyder found that as seen by somebody riding in the cloud, it collapses to r equals 0, 0 radius, and infinite density in a finite and short time. But as seen from outside, the cloud becomes frozen forever at the Schwarzschild radius at r equal 2m. And what was really going on and how these two different points of view were compatible with each other was a huge mystery. I discussed this with Yevgeny Lifshitz in 1982. He was a close personal friend. He and Landau had been in Moscow. They read the Oppenheimer-Snyder paper in 1939, and he describes their reaction. You simply cannot appreciate how difficult it was for the human mind to understand how both viewpoints can be true simultaneously. That's a quote from a tape recording that I made of a conversation with Lifshitz in 1982. What was really going on did not become clear and fully understood until much later, up in the late 50s and early 60s, as a result of work by a number of people, such as Finkelstein, Beckendorf, Misner, Kruskal, Wheeler. We nowadays draw a space-time diagram of the collapsing shell of dust with light cones on it, plotting Eddington-Finkelstein time upward and Schwarzschild radius outward. And we all know that the light cones tip over, so at the horizon there are light rays that travel straight up the horizon, and that the region that is left behind here is the black hole inside the horizon. But the question I want to ask about this, once it became clear what was going on in that collapse to form a black hole, what is it that generates the black hole space-time curvature? The black hole is up here. This may be 1 million years after the star collapsed. Let's talk about it when the black hole is 1 million years old. You're way, way up there. And so the space-time curvature is surely not generated by the singularity that's at r equals 0 along this line, because the singularity is out of causal contact with the exterior. So singularity can't be responsible for the space-time curvature. The star that collapsed, well, it's in causal contact because if you had a recording of the history, you could you have that information. In principle, you could look back and see it, but of course the problem is that, that the light that was emitted by the star is quantized, discrete photon. The last photon that comes out roughly a day after the collapse, a very, very short time. And so you don't really see it back there. And so I don't think you can argue in any reasonable way that the star is responsible for this. The star by now, in any reasonable slicing of the space-time, the star has gone into the singularity. And the matter is all gone. And so I think the only reasonable answer as to what generates the space-time curvature is that the curvature is generated by the curvature's energy. And of course, you can formulate the vacuum Einstein equations in that way. You can formulate them with basically a wave operator acting on the metric on the left-hand side, pull that linear piece out, and on the right-hand side, you have a number of nonlinear terms that can be interpreted as the energy or the stress energy pseudotensor, if you wish, of the space-time curvature. But it's curvature generating curvature through nonlinear interactions. In that sense, the black hole is a gravitational soliton. Though we have not often talked about it in that language, and I don't know when or to whom this way of thinking about it first became clear. I've sort of thought about that way for a long time, but not very explicitly until recent years. And the idea of the black hole as a gravitational soliton, you don't find that word, that phrase in the literature much, if at all. I don't know of it anyway. And I think it'd be interesting to probe in and see to what extent and in what manner this idea has come into being. So let me talk about geometry. So backing up, the black hole as a gravitational soliton, it's something that we've known for a long time, but it is a stationary solution of the Einstein equations, the Schwarzschild solution or the Kerr solution. And what I'm really interested in is geometrodynamics, nonlinear dynamics of curved space-time. And so the first example of this that was really explored and came to be understood, as far as I'm aware, was the geometrodynamics of space-time curvature near generic singularities. So some history of this. In the late 1950s and then reaching fruition in the early 1960s, in Moscow, Isaac Kalatnikov and Yevgeny Lifshitz, inspired by Lev Landau in discussions with Landau, who had been their mentor, they asked themselves, can we construct a generic space-time singularity? And their concept of genericity was that you could give the full set of initial data for the vacuum Einstein equations or the Einstein equations with some chosen form of matter, give a full generic set of initial data, and it would evolve forward and produce a singularity. And so they would count numbers of degrees of freedom in the initial data and see if they could build initial data that was fully generic in terms of the number of free functions. And then it would evolve to a singularity. And they searched and they searched and they searched, and they could not find any generic space-time singularities of that sort. And so they memorialized this, Landau and Lifshitz, in the 1962 English edition of Classical Theory of Fields. There's the last section, as I recall, of the whole book, if my memory is right, is a proof, or quote proof, proof by inability to find a solution, that there are no generic solutions with space-like singularities. And I remember reading that and puzzling over it in that period. That book was the first book on relativity I tried to read. It was only later that I discovered that you can never understand anything that Lifshitz writes in terms of textbooks, and it was Lifshitz who wrote these textbooks, until you already know the subject, and then you can understand it. And for the person who already knows the subject at a modest level, they are tremendously powerful textbooks. But for a novice, almost impossible to understand. So I puzzled over that. 1963, Penrose and Hawking began to develop singularity theorems. And Penrose for singularities inside black holes, Hawking for cosmological singularities. This was an effort, singularity theorems, that began in '63 and extended on into the 1970s. And they proved that generically, inside a black hole, or under reasonable assumptions in cosmology, you have to have singularities in the sense that causal curves end, time-like curves and null curves end. The manifold cannot be extended to infinite affine parameter along a causal curve. This produced great consternation and confusion because of the conflict between the Kalatnikov-Lifshitz results and the Penrose-Hawking results, especially in Moscow. And I remember particularly the GR4 meeting in London in summer of 1965. I'm almost sure I have the proceedings of the meeting, which don't exist online. I have them on paper at home. And unfortunately, I didn't dig into them before I came here. So my memory is that Lifshitz and Kalatnikov were both there, that Hawking and Penrose gave talks about these singularity theorems, that they argued against this, that we have proven that there are no generic singularities. You have theorems based on topological methods that say that causal curves end, but they don't say what happens and why the causal curves end. And then you have this failure to find any generic singularities in the sense of divergence of the Riemann curvature tensor. So Lifshitz and Kalatnikov went back to the drawing boards after that. And finally, in 1969, working with Belinsky, Kalatnikov and Belinsky together found the error in the previous analysis. And they found, in fact, a solution, a singular solution of Einstein's equations with a space-like singularity that is generic in terms of the numbers of degrees of freedom in the initial data. 1971, I was in Moscow, and Yevgeny Lifshitz, who joined in on this work late on after Belinsky and Kalatnikov had found the error, he came to me with a manuscript for Physical Review Letters, which is basically a mea culpa by Kalatnikov and Lifshitz, saying we were wrong, and here's why we were wrong, and here's what the generic singularity looks like. He asked me to carry it out and submit it to Phys.Rev Letters because it took so long to get things through the censors in the Soviet Union in that era, and he didn't want to have to fight with the censors. And so I carried it out and submitted it in their behalf to Phys.Rev Letters. And they forthrightly said, well, here was our mistake. And in fact, there is a generic singularity. The analysis that enabled them to find this generic singularity was made possible by their discovery that as you approach this particular space-like singularity, there was a spatial decoupling that neighboring observers or neighboring time-like world lines or geodesics approaching the singularity would lose causal contact with each other ultimately when you got close enough to the singularity. And so pick any two time-like geodesics approaching the singularity, say initially parallel, and due to geodesic deviation, they will get pried apart sufficiently far before you reach the singularity that they'll have no more causal contact. And this enabled Belinsky, Kalatnikov, and Lifshitz to decouple the Einstein equations turn them from partial differential equations into ordinary differential equations. And then they could solve the ordinary differential equations by various standard techniques. And they discovered that the temporal dynamics along any one of these world lines is what's called a mixed master behavior, that I'll just remind you what that is in a moment, which had been discovered by Misner and independently by Belinsky and Kalatnikov in the homogeneous situation. And they found also that matter with pressure less than energy density has no influence on this, that it's the vacuum dynamics that are controlling this approach to the singularity. Now, it's quite interesting that this analysis that they gave produced enormous skepticism in the West. This came to be called the BKL, for Belinsky, Kalatnikov, Lifshitz, conjecture. And the arguments for it were called heuristic arguments, quite uniformly among relativists in the West. So I'd like to make some comments on level of rigor that's required by different communities of physicists. I'd like to hark back to the quotation from that I've forgotten, maybe it was Jürgen did, of Richard Feynman writing to his wife. Was it somebody talked about? Yeah, Roberto. Yeah. So Richard Feynman writing to his wife from the Warsaw Conference about the dopes there. There was a huge cultural difference between Feynman and almost all of the relativity community in terms of the level of rigor that they thought was needed to prove things. And so Feynman felt they were just trying to prove things that were obviously true. That was one of the issues that Feynman had with the community. He was happy with a much lower level of rigor than they were. And I found this also myself coming out of the Wheeler School, a rather more physical point of view. I also, in the period that Dan Kennefick writes about in his book, about trying to understand gravitational radiation reaction, it seemed to me quite obvious. The Landau-Lifshitz demonstration of that you do emit gravitational waves and there's radiation reaction, that seemed to me to be just fine. It was clearly right, and how could anybody argue with this? But within the relativity community, very few people had that attitude. And so I was probably viewed as very arrogant at the time, as was Feynman. And similarly here, in my arrogance, I thought, well, my colleagues here in the West are just asking for a level of rigor that is not reasonable in physics. And so I, throughout that period, continued to regard this and call this a BKL demonstration of generic singularity, not a heuristic arguments and not a conjecture. Just to remind you, and this is the really important punchline from the point of view of geometrodynamics, the dynamics, this mixed master dynamics that the space-time curvature follows along the world line of anybody approaching that singularity is chaotic. It's described by what's sometimes called a continued fraction map, and that's a map that is highly sensitive to initial conditions, is chaotic in the sense of chaos that's normally used in mathematics. In particular, if I plot at any moment of time, as you approach the singularity, you have a tidal stretching along one direction and squeezing along two orthogonal directions. If I call east-west the direction of tidal squeeze, there, along the east-west direction, you have a continual squeeze for some time through what is called an era, and then suddenly there's a jump, and the east-west direction starts to oscillate. During this first era, the up-down direction and the north-south direction, they oscillate between stretch and squeeze. And then you go to the next era, and which direction is a continual squeeze and which is a stretch and squeeze is different. And you go from cycle to cycle, cycle, cycle in a change of era, and the entire pattern, as I said, is governed by a chaotic map. So this was the first, for me, the first real demonstration of interesting nonlinear dynamics in curved space-time, that you can get chaos here as you get in other nonlinear systems in physics. Okay. Now, the people in the West said, look, this is just a conjecture. We have to test it. We don't have the tools to do it analytically, so we will do it numerically. So this was one of the first numerical relativity programs to get at nonlinear dynamics of curved space-time. The program was formulated by Beverly Berger and Vince Moncrief in 1994, carried out by them, Garfinkel, Eisenberg, Weaver, 94 onward, and then there were subsequent analytical studies. The bottom line was that BKL was largely confirmed, but there was something missing. So I was probably too arrogant in my attitude. There was something missing. From one point of view, it's just a little bit of frosting on the cake. From another point of view, it's fundamental. But there are spikes in this dynamics that occur, spikes in the stretching and squeezing, that occur on spatial two-dimensional surfaces that reside in three-dimensional space. They recur more sharper and sharper at late times, and they actually can occasionally modify the chaotic map. And so it really was true that BKL had missed something. They had the large-scale picture, but there were details, important details that were missing and that could only be gotten at through numerical simulations. Now let me talk about generic singularities inside black holes. I'm going to tell you the story of this quickly in terms of the usual way of approaching it with Penrose diagrams. We have our universe. This is a Kerr black hole, the global structure. For those who aren't familiar with this, I'm going to give you a very different point of view on it in a moment. This is our universe. Here's the event horizon of the black hole, future time like infinity, past time like infinity in our universe. Inside the black hole, there are two Cauchy horizons, and then the pattern continues on. If you have a star that gravitationally collapsed to form a spinning black hole, away from the star's surface, if you get far enough to the right, this becomes the Kerr metric. It settles down into the Kerr metric. And so I use this same diagram, and I just recognize that in the vicinity of the surface, the geometry is not Kerr, but I get above the surface a little ways, and it is Kerr. A number of people have done perturbation analyses, not numerical relativity, just perturbation analyses, to try to understand what happens at these Cauchy horizons in the Kerr metric. And Poisson in Israel in 1989 discovered that this Cauchy horizon is unstable, and basically all of the stuff that falls into the black hole in the entire future of the universe piles up near this Cauchy horizon and produces a sort of a shock wave, the Cauchy horizon of divergent Riemann curvature. And then very recently, Ori, Perron, Marolf have recognized there's a similar shock singularity along that Cauchy horizon. Now, as you may know, I was involved in a movie recently called Interstellar. And in connection with the Interstellar, I've written a book about the science in the movie. When I was brainstorming for the movie with Christopher Nolan, who wrote the final draft of the three drafts of the screenplay, we together decided we would let Cooper, played by Matthew McConaughey, fall into a spinning black hole and encounter singularities. There are three singularities here: the BKL singularity, the shock singularity, the mass inflation singularity. And since I wrote a book about the science of Interstellar, I had to visualize what this looks like. And this is really a lesson to me, a reminder to me, of the power of the requirement to try to explain something to a more general audience. So I'm going to show you my visualization of what these singularities look like. This is just a still from the movie. You can't see it very well, but Matthew McConaughey is falling into the black hole. He's inside the horizon. He's looking out at the external universe. And this is the accretion disk around the black hole. The external universe is inside the accretion disk, and the black hole is outside it. If you think about it, that's what it is really like. if you're down inside the black hole. These images were produced through solving ray tracing or light beam tracing equations in the Kerr spacetime. Here's an embedding diagram showing the geometry, the usual trumpet horn geometry for a rapidly spinning black hole. The horizon is here. Here is McConaughey and his spacecraft falling inward. Here is the BKL singularity, stretch and squeeze in a chaotic manner. And what happens is that he has fallen in here. He has a few minutes until he's going to hit the singularity. And all of this stuff that will ever fall into the black hole in the future falls in after him, and because of the time dilation, gets squeezed into a fraction of a second. So a very thin sheet falling down, chasing him down into the black hole, and that's the mass inflation singularity. At the same time, all the stuff that fell in before him, some of it scatters back up, and that also piles up. This is just to say that this mass inflation singularity is integrable. The first time integral of the Riemann tensor is finite, so the amount of stretch and squeeze that the McConaughey experiences is finite when he hits the singularity. So it's conceivable he might survive. All the stuff that fell in earlier, some of it backscatters and creates an outflying singularity, the so-called shock singularity, and he's sandwiched between those two singularities. And that's what happens in the movie. And he gets scooped up by something called a tesseract at the outflying singularity, and the movie goes on into its Kubrick-like conclusion. But this is the nature of the interior of a black hole as we currently understand it. But through perturbation theory, here we have numerical simulations. This is just perturbation theory, and nobody has solved Einstein's equations for the interior of the black hole numerically to see whether this is the correct prediction. Yeah.
I'll be asking a stupid question, but because I've seen the movie twice, do we see this both from this perspective and from his own perspective, or only from his own?
Only from his own perspective.
But this is not from his own.
This is not his own perspective. Right. This is the perspective of my book.
Right. Yeah.
But this is the conversation that Christopher Nolan and I had when he was writing that part of the screenplay.
So we never see it from the classroom perspective?
No. So let me turn to nonlinear self-coupling of gravitational waves. How am I doing on time?
As long as you need.
Well, I want to know.
Because you've been talking for 48 minutes.
Okay, fine. So nonlinear self-coupling of gravitational waves. This is famous work by Matthew Choptuik, 1993. Here's my heuristic description. You have gravitational waves that implode. They interact with themselves. And if you fine-tune the amplitude of the gravitational waves just right, you develop a discretely self-similar structure in here so that you get gravitational waves of a particular shape coming out on shorter and shorter length scales or higher and higher frequencies, what I would like to call an organized frothing. And what Matt discovered, again through numerical simulations now on a computer solving the axis-symmetric geometrodynamics, was that the behavior that you get is reminiscent of phase transitions in condensed matter. He originally did this with a scalar wave. I'm going to skip over this. More interesting for geometrodynamics is the case of a gravitational wave, which was worked out by Abrahams and Evans shortly thereafter, and then in greater detail by Sorkin in 2011. So you imagine you have an imploding gravitational wave. You have carefully tuned the amplitude of the wave so that it will either just barely make a black hole because it just barely has enough energy to do it, or it just barely won't make a black hole. If the amplitude is bigger than a certain critical value, then you get a black hole, and the mass of the black hole scales as the difference between the actual amplitude and the critical amplitude. raised to a power beta, which is about 0.38 in both the scalar and the gravitational wave simulations. There's universality to that exponent. If the amplitude is a little bit less than the critical value, then the space-time curvature turned it into something that also has dimensions of length in geometrized units. Scales in precisely the same way, the same power law. So this is reminiscent of phase transitions in condensed matter. And CHOP2X saw very clearly this discrete self-similarity in the scalar field case. And in Sorkin's more recent simulations, there's strong evidence that this is also discretely self-similar. So we've now seen in the BKL singularity chaos, we have seen in this critical phenomenon business, we have seen condensed matter type phase transitions as you go from an amplitude of wave that is below to above the critical value. I think that these numerical studies are really in their infancy. We're just beginning for the first time now to uncover the richness that can occur. Another place where we've seen interesting phenomena is in higher dimensions, a black string, which is an analog of a black hole in 4 space and 1 time dimension. Here is the string. This is a numerical simulation by Luis Lehner and Franz Pretorius. Here is the string. It's going to collapse inward on itself. It has a cross-section that is spherical, like a black hole, and then a translation in that 5th dimension, in the additional space dimension. As you watch it, it breaks up into black holes with a string in between, and then the string breaks up into black holes with a smaller string in between, and then that smaller string breaks up into black holes, and in a finite time, you get an infinite cascade in these simulations. An infinite cascade going to smaller and smaller, thinner and thinner strings, and more little black holes.
Is the time unit years?
So that time unit, I think, is proper time is seen somewhere. It's basically proper time. But it's whatever coordinate time they're doing the integration in, but it's more or less proper time, as I recall. So in a finite proper time, you actually go to a singular structure that has this kind of a successively smaller and smaller strings connected to black holes. This is in higher dimension. This is not what occurs in our universe, but it illustrates the richness that can occur in geometrodynamics. I want to wind up with geometrodynamics in binary black holes. This is the area that I've been working in more recently. This is the standard, a well-known simulation in which you watch 2 black holes spiral together. This is an embedding diagram, basically, in which you're seeing the spatial curvature in these throats. You're seeing the lapse function, or the slowing of time in the colors. And the arrows are the shift function, or basically the dragging of space into motion. And you watch in the simulation by the Caltech Cornell CETA collaboration, you see the merger of the black holes, and then you see it settle down. So this was exciting when this was first done. But the problem with this is that you do not see very much of the space-time curvature. You don't see the gravitational waves. You see basically 3 scalar quantities embodied in the depth of the shape of the surface. That's 1. It's basically the scalar curvature of space-time, of the 3-dimensional slices of space-time. You see in the color, you see the lapse function. In the arrow, you see the shift function. You don't see the gravitational waves. There's lots of other stuff that you don't see. And so in order to understand geometrodynamics visually, the students and postdocs I've been working with decided we needed a visual representation of the full Riemann tensor. And so we slice space-time into space plus time, as is always done in numerical relativity. When you do that, the electromagnetic field tensor splits up into the electric field and the magnetic field, which we visualize by field lines. The electric field lines between a positive and negative charge, magnetic field lines around the Earth. So that's electromagnetic theory that we're all familiar with. The Riemann curvature tensor, when you do this splitting of foliation of space-time into space-like hypersurfaces with time flowing between them, Riemann curvature tensor splits up into what's sometimes called the electric part and the magnetic part. These are symmetric trace-free tensors that live in the space slices. In particular, the electric part in the reference frame of a freely falling observer, say, who is passing through that slice, that's the space-time part of the Riemann tensor. It's the piece that produces the stretching and the squeezing. So that in particular, if you have two freely falling particles separated by a vector c, the relative acceleration of this particle p relative to q is minus the contraction of the tidal tensor ejk into the separation vector. That's geodesic deviation. The magnetic part is the dual constructed with the Levi-Civita tensor, and then the space-time piece after you've taken the dual. And that describes differential frame dragging. So that if you have a gyroscope at Q that you use as an inertial reference frame and a gyroscope at P, the gyroscope at P will precess with some angular velocity delta omega relative to that at Q. Delta omega is the contraction of this so-called frame drag field into the separation vector. So you have these two pieces. One is tidal stretching and squeezing. The other is differential frame dragging. We can visualize these fields by constructing first the eigenvectors of these symmetric trace-free tensors, and then the integral curves of the eigenvectors, which we color by their eigenvalues. And so this is an example that I'll talk about in a moment, where you have then a network. There are three eigenvectors, so there are three orthogonal families of field lines. Here you just see in the equatorial plane of a perturbed black hole, you see two sets of field lines, red and blue. They're orthogonal to each other. And they carry the information about the Riemann curvature tensor. And so we have a way then to visualize the Riemann curvature tensor. And I want to just give you just a little bit of sense of what we've been able to see in geometrodynamics from it. So if I have a Kerr black hole, and I place a person, I put Diana here above the north pole of the Kerr black hole. Her head looks down at her feet and sees her gyroscope at her feet precessing relative to the gyroscope at her head with an angular velocity that's proportional to her height. And so I divide that by the height, and I get the normal component of the frame drag field. And so that represents the differential frame dragging that she experiences. At the north pole, her feet are dragged relative to her head in a counterclockwise way, the south pole in a clockwise way. And this is symmetric. If you take a wet towel and you try to wring the water out of it, your left hand sees your right hand turning clockwise, your right hand sees your left hand turning clockwise. So there's a clockwise, in the North Pole there's a counterclockwise, basically vortex, we call it a vortex. Its horizon vorticity is the normal component of B. And the South Pole, there's North Pole is counterclockwise, South Pole is clockwise, red is counterclockwise, blue is clockwise. A horizon vortex is a region with high vorticity. So if I look then outside the black hole, in fact, you have, through any given point, you have three sets of vortex lines, which are the integral curves of BJK, the integral curves of the frame drag field. Coming out of the North Pole, there are red vortex lines. They come out, they swing around and go back into the North Polar region. And along those, Diana will be twisted counterclockwise. Coming out of the South Polar region, there are clockwise vortex lines, and then spiraling around and around, there are clockwise vortex lines. And so this is the structure of the Riemann curvature tensor, of the magnetic part of the Riemann curvature tensor, the frame dragging part around a Kerr black hole. A region with large vorticity, large values of the large numerical values of the eigenvalues of B, we call that a vortex. It's a vortex of twisting space. So now let me show you some geometrodynamics. I have here two black holes, one with its blue vortex line sticking out of the top, the red vortex line sticking out of the bottom. This one is inverted, and they're going to collide head-on. I'm going to remove the vortex lines and just show you the horizon vorticity, but wherever you see blue, there are blue vortex lines sticking out. The two black holes merge. This is the absolute event horizon. We now have 4 vortexes attached to this black hole. And these vortexes robustly retain their individuality. So you've got vortex lines, 4 sets of vortex lines coming out of the black hole, twisting along each of these. Now let's watch what happens in a collision. And watch carefully. This is blue on the right-hand side, the upper right-hand side, red on the upper left-hand side. It merges. The vorticity goes away. Suddenly it's recreated red here, then recreated blue here, then recreated red here, then recreated blue here. What's happening is that these vortexes are interacting with each other. The clockwise vortex and the counterclockwise vortex, they interact with each other and they exchange vorticity. So that the one that was going clockwise flips around and goes counterclockwise. Then it flips around and goes clockwise. And whenever the surface of the horizon appears green, at that point, there are no vortex lines on the black hole at all. And so, in fact, at the moment when you have a bright blue vortex up here and a red vortex there, the vortex lines go from the red vortex here around onto a red vortex on the back side. Blue vortex lines go around to a blue vortex on the back side. In the oscillation, when the horizon turns green, the vortex lines detach from the horizon and join onto each other in closed curves, producing a toroidal ring of frame-dragging vorticity that travels out from the merged black hole at the speed of light. And as it travels outward, it generates 10-dex lines. 10-dex lines are integral curves of the eigenvectors of the tidal field. It generates these 10-dex lines that squeeze Diana along this direction and stretch her along that direction. And so you have this torus of intertwined, twisting vortex lines and stretching and squeezing 10-dex lines. And that is the nature of a gravitational wave. It travels outward, it becomes a gravitational wave locally. You have then stretching and squeezing along these directions. And I've just pulled that off to the side. That really, these should be superposed. You have you have the twisting along those 10-dex. Stretching and squeezing along the 10-dex lines, twisting along the vortex lines. In the more realistic case of an inspiraling collision, what happens is that the vortex lines stick out of the black hole and swing around like water from a whirling sprinkler. And you wind up with a spiral arm type structure of vortex lines and 10-dex lines. This gives you some sense of what happens then in geometrodynamics in colliding black holes. You also have, when the two black holes merge, you have 10-dex lines that stick out of the ends here that are stretching 10-dex lines, and you have squeezing 10-dex lines around the equator. And as the black hole tumbles, having merged with the two black holes going around each other, as the merged black hole tumbles around, these reach out in a spiral arm structure similarly. and they generate attached or coincident vortex lines. So again, you get a gravitational wave structure. So there are two types of gravitational wave structures. One generated by vortex lines that are attached to the black hole, and the other by Tendex lines that are attached to the black hole. Well, I'm going to stop at that point. I've used up more than my share of the time, except to just remark, I wonder if the remark is, yeah, the remark is here, that our goal then, my personal principal goal in gravitational wave astronomy is to build at least 1,000 simulations of black holes with different spins and different orientations, different relative masses, and get a catalog of waveforms to go along with the dynamics of the vortex and the vortices and tendencies of the black holes. So we have a dictionary so that when LIGO and its international partners detect gravitational waves and start measuring waveforms, we can go back from the waveforms and deduce what's going on in terms of the nonlinear dynamics of curved space-time, the geometrodynamics of vortexes and tendexes attached to black holes. Okay, thanks.
Forgive me, you say the...
Please use the mic.
How far can a coordinate transformation take you in order to, say, remove the vortex field and get mostly Tendex lines? Is that?
So the vortex lines and Tendex lines being...
Speak to them, please.
I'm sorry. Since the vortex and Tendex lines are actually features of the Riemann curvature tensor, you don't get rid of them at all by making coordinate transformations. You don't even need a coordinate system, particularly in your spatial slices. These live in the spatial slices. You have to do a slicing. And so there is where the dependence on the time coordinate comes in. You have to do a spatial slicing before you can split the Riemann tensor into these two parts. But once you've done the spatial slicing, these are field lines, like the electric and magnetic field line, live intrinsically in that space slice, and you don't even need coordinates in order to discuss them and visualize them. So then the more precise worry or concern there is to what extent does what you see depend on your slicing? And this is not fully explored, but the indications are the following. This is what I expect in my arrogant way as a not very mathematical physicist. That when people do numerical simulations on computers, it's very hard to get the simulations to go successfully. And although they use very different techniques and very different methods of choosing their slicings, I think they are driven to more or less the same kinds of slicings. Otherwise, the simulations crash. All I can say is that we don't see much sign of slicing dependence, but it is not very well explored at all. You could ask the same question of electric and magnetic field lines and their dependence on slicing. It's in the mathematics, in an inertial reference frame, the mathematics of the Bianchi identities looks very much like Maxwell's equations. And so you really are dealing with very, very, very similar mathematics and structures in that sense. Yeah.
I have one interpretational question and a historical comment. Mm-hmm. So first, the question. The splitting of the Riemann tensor that you presented into a tidal field and a frame dragging field. Would you say that the analogy to the electromagnetic split to the Faraday tensor into electric and magnetic component really goes so far that you could say the tidal field corresponds to the gravitational aspect of the Riemann tensor and the frame dragging field to the inertial aspect, which are of course unified in the Riemann tensor? Or do you think it's not as neatly?
I would have said, I don't know how to interpret the frame drag piece Well, I guess it's inertial in some sense. It's inertial associated with rotation. Mm-hmm. So I guess you could discuss it that way. I've not thought about it that way. It's, this splitting has been done for decades. You find, for example, in that classic compendium of articles put together by Lou Witten in the 1950s, or maybe it was 62, you find this discussed. And it was generally discussed, these as the quote electric and quote magnetic parts of the Riemann tensor. And that's the way people have normally thought about it. But your way of describing it, that sounds plausible as well, and maybe that would be a fruitful direction to pursue it. Yeah.
Thanks. And just very quickly, the historical comment on geons. You remember in Wheeler's autobiography, he reports of this one telephone call that he had with Einstein, where he says, I told him about geons, and Einstein was instantly in the early days, right? Mm-hmm. Einstein was instantly skeptical that this would be a stable solution. And of course, much later, I found out that he was right, and that only shows that he reacted so quickly on this and doubted the stability, that his enormous physical intuition, blah, blah, blah. But one interesting parallel that Wheeler wasn't aware of was that this wasn't very quick physical intuition that Einstein had. Einstein tried to find something very, very much like a geon solution already in 1919, where he had a very slightly modified Einstein equation with cosmological constant, and he tried to find solutions that would almost Einstein-Maxwell equations, and tried to find spherically symmetric solutions that he could interpret as a particle that is a composition of electromagnetic and gravitational fields. So exactly the same idea as the geon. And this idea was one, if not the guiding idea for much of his unified field theory research, right? You can really see that whenever he abandoned a particular approach to unified field theory, it was because he convinced himself that he couldn't find such a solution. So there's a very interesting comparison there between that work of Einstein and Wheeler's geon work, and it would be quite interesting to look at the geon work and see how far this parallel goes, also on a mathematical level.
So presumably Einstein also knew that the solution he used in 1939 for the photons running around a sphere, that's unstable. He must have.
Yeah, that's also connected to that.
Though he doesn't make any remark to that effect in the paper, as I recall. But,
On a more trivial point, in also Einstein in 1923-24, in the volume that we're publishing next week, spends a lot of time on geomagnetic experiments within the framework of his unified field theory. So he tries to explain the magnetic field, both solar and terrestrial. Am I right, or am I saying nonsense?
No.
Both the solar and terrestrial magnetism by first trying the affine connection, seeing if that leads him somewhere, abandoning that, carrying out experiments with Picard over a long period of time. This is the kind of work I didn't have time to talk about on Monday morning. Numerous experiments, and if you're interested, I will send you the PDF, because I think it's very pertinent to this.
That sounds fascinating.
He abandons everything. He tries to say, well, maybe geomagnetism is due to the difference between the charge of, electron and proton, and does these experiments and abandons this work. So again, unpublished work, but along these lines. Mm-hmm. We know that, but we can't prove exactly his thought processes, but it is this.
Yeah, I think one important aspect there is that he thinks that in a unified... that in a unified field theory, you would expect something similar to electromagnetism, that, if electromagnetic and gravitational inertial fields are really two aspects of one total field, then you would expect that a rotating electrically neutral but gravitationally charged charge, so a neutral mass, could possibly produce magnetic fields in some regime. And that's why he thought, well, so the Earth is not electrically charged, but it is a gravitational charge. If electromagnetic and gravitational fields are two aspects of one total field, it should be possible to produce a magnetic field by just rotating a gravitational charge. And that's very difficult to pin down, as Diana said, in the papers that he published, but it seems to really be in the back of his mind that something like this should happen.
just a footnote to this discussion. This, of course, goes back even earlier to the attempts to do a nonlinear electromagnetism, which Einstein started around 1909, trying to create such soliton-like solutions within a nonlinear modification of Maxwell's equation. But I had more future-oriented questions, namely, you told me also in personal conversation that this has also an intrinsic interest, and to follow the nonlinear dynamics with this program, not just.
That's where my own interest is, in fact. And to me, the most, aside from the possibility that gravitational wave detectors will see something totally surprising that revolutionizes things, that's the most interesting thing. The second most interesting thing is exploring the geometrodynamics, the intrinsic geometrodynamics observationally.
Yeah, and I have a question that may also build a bridge to the next talk in a way, because we have on an axiomatic basis a fairly good understanding of quantum fields in curved backgrounds, and we have the iconic Hawking results and so on. Wouldn't it be interesting, again, not for observational purposes, of course, but to understand the nonlinear dynamics, to add quantum effects to this, but not in the sense of a quantized gravitational theory, but just external quantum fields, into these nonlinear dynamics, to just see what kind of new phenomenology might turn out from that. That would be a whole program along those lines, but with an added twist.
Yes, I agree. Nobody that I know of has looked at that at all.
Yeah, so I'm suggesting this now.
Go back up.
Thank you very much for your instructive talk, and I would like to come back to your categorization of the difference of understanding, and it's an historical question, of understanding of, or view of what rigor means in a particular community that was forming in that period. That is close to what I was looking into, that was a kind of standards that they were searching at the time. So it might be possible to say that a certain community of physicists at that point came to recognize that mathematical rigor was important in order to obtain physical insight, and if yes, when, if you have a view at this point.
Yeah, so somebody that comes to mind who I was very close to is Chandrasekhar. Chandrasekhar had very little physical intuition. He was a close friend. I know this well, but he was superbly good at pulling physical insight out of the mathematics. But he insisted on real mathematical rigor, because that was the way he made his progress, was being as rigorous as possible and then getting the physics out of it. So he never felt comfortable at all with the proofs of the stability of black holes that were based on numerical solutions. He wanted a rigorous mathematical proof. So he sits there side by side with, in the same community as Wheeler or me, who completely comfortable with numerical solutions and numerical proofs, and ready to search for answers through physical arguments. Another example, again sitting in the same community, but the same person at different times, Stephen Hawking, when he was working on singularity theorems and global methods, he was highly rigorous. And the book of Hawking and Ellis is, of course, is the paradigmatic example of this. You find him in the late 1970s now working in quantum gravity and making statements or claims without very much justification. So I asked him around 1977 or 78, what's going on here? You've abandoned the level of rigor you used to have. And his response was, I'd rather be right than rigorous. Life is too short, maybe shorter, we thought shorter for him than other people, it turns out not. But life is too short, I want answers, and I'm only going to get answers to the deep questions I want to explore by dropping the rigor. I do think that it is true that in physics you need both, but the kinds of insights that Hawking had later in his non-rigorous era, or that Johnny Wheeler had, that come from physical arguments to a great extent, lesser extent from mathematics. Those are crucial for moving the boundaries of knowledge forward, but the rigor is absolutely necessary as a check on the claims and the insights that are being had. And I do think that the BKL example that I gave is really a good example where I think to anybody who thinks about physics as I do, that it was clear that they were right. In fact, they weren't quite right. They missed something that the rigorous people picked up. So within a community, you need this mixture, but it's also true within the relativity community, the two different pieces of the community, the intuitive piece, I would call it, and the rigorous piece of the community, there's a certain tension between them, a certain disdain even between them for how the other side is proceeding. But nevertheless, when you step back and look at it, you see that both are absolutely essential to progress.